家や地域の分断が深刻な時代です。だからこそ日本とヨーロッパが協力したEarthCareは異なる地域が共に同じ目標に向かっていける希望となり得ると信じています。Thank you.
I couldn't agree more. Shaping a future is up to us. Thank you very much, Takaguchi-san.
分断が深刻な時代です。だからこそ日本と
And
ヨーロ
now,
ッパが
let's go
協
over
力
to
した
Dominique Giron
EarthCare
from
は
ESA.
異なる地域が
Dominique,
共に
what have you taken
同
away
じ
as a
目標
benefit
に
from
向か
this
っていける
cooperation between
希
ESA
望
and
と
JAXA?
なり得ると信じ
So
てい
the
ます。
first obvious one
I couldn't
is
agree
to
more.
get
Shaping a
the best
future is up
technologies
to us.
from
Thank you very
Europe
much,
and
Takaguchi-san.
Japan to
分断が
do
深
this
刻な時代です。
extremely challenging
だからこ
mission.
そ日本と
And now, let's go over to Dominique Giron from ESA. Dominique, what have you taken away as a benefit from this cooperation between ESA and JAXA?
なり得る
On
と信じ
this
て
first obvious cooperation
I couldn't agree more. Shaping a
resilience, the best
future is up
technology
to us.
from
Thank you very much,
and
Takaguchi-san.
Japan, as we have extremely challenging mission from the
And now, let's go over to Dominique Giron from
and
ESA.
from time to
Dominique,
time,
what have you
it was
taken away as a
so
benefit from this
critical
cooperation
that I
between ESA and
wonder
JAXA?
if my partner will continue to follow me.
I couldn't agree more. Shaping a future is up to us. Thank you very much, Takaguchi-san.
Okay, guys, it's just too much. We know but they never
And now, let's go over to Dominique Giron from ESA. Dominique, what have you taken away as a benefit from this cooperation between ESA and JAXA?
and my partner will continue to cooperation from
I couldn't agree more.
them, and that's what I keep in mind for this cooperation.
Fantastic. That is so nice to hear. Thank you, Dominique.
The industry contract to realise EarthCare was signed back in 2008 with prime contractor Airbus Germany. Here we see Angela Merkel and Volker Liebig kicking off what would become a mammoth project, starting with the spacecraft platform in Airbus UK, while in France and Italy, Airbus and Leonardo worked together to build the giant LiDAR instrument, while across the globe in Japan, JAXA led development of the CPR Doppler radar. Back in the UK, Thales Alenia Space UK and Surrey Satellite Technology built the two remaining instruments, the broadband radiometer and the multispectral imager. Overall, 75 industry partners from Europe, Japan and Canada have contributed to make EarthCare happen.
You won't find an ESA member state that isn't involved in this mission. And together with the Japanese partners, all the bits and pieces came together and have finally been assembled at Airbus in Friedrichshafen. A large white satellite with a large solar panel. And now we are joined by Albert Saklauer from Airbus, the prime contractor. Albert, the satellite has a new UV laser and needs to fly in a lower orbit than usual, and here it faces more atmospheric friction. Is that a problem for the mission?
Well, we would not call it a problem, we call it a challenge for engineers, and engineers love to be challenged. So our solution on this is that we made a very slim design, a very compact one. I would call it even a compact car compared to a compact car. 4 very important passengers on board, going with very low fuel consumption. And the trick is that we do a very low cross-section and we keep the solar ray in the shadow of the body. And so we can fly this mission on this orbit.
Fantastic. Well, it's impressive engineering indeed. Let's now take a look back to our launcher as it stands and is ready to go on its launch pad. Thank you, Albert.
And everything is looking good at our launch site in Vandenberg with less than half an hour of the countdown to go. An ESA team is, of course, out there in California, and one of them sent us a message from the launch pad earlier today. Let's hear from Dirk Barnards, the EarthCare project manager.
Good evening, everyone. I'm super excited here to go in a few minutes to the Launch Control Center to launch this incredible mission, EarthCare. We're at this point with the satellite fully ready for launch, with the rocket fully ready for launch. And all this thanks to the very hard work of teams here in Vandenberg over the last few weeks and months, but also in Europe, in ESOC, in Japan, all over the world. Not only over the last few months, but over many, many years. And I know many of you are actually in the audience, and I cannot thank you all enough for the dedication and the very hard work that you did to bring this incredible mission to the point where we are now.
And here in ESA Mission Control is where EarthCare will be operated from for its entire lifetime, 24/7, around the clock. And I'm happy to report, as you can see there, that the board is green, and at this time here in Mission Control Darmstadt, we are go for launch.
EarthCare carries 4 state-of-the-art instruments. Its multispectral imager will provide an overview in multiple wavelengths to set the scene. The cloud profiling radar will detect vertical motion within clouds, providing details on their internal dynamics. Its atmospheric LiDAR will detect the top of clouds and provide profiles of the atmosphere with information on aerosols. And its broadband radiometer will measure the reflected sunlight and heat radiated from Earth. Together, these instruments form a powerful suite of tools that will provide unprecedented observations of Earth's atmosphere.
With me now is Kotska Wallace. Kotska, you were originally a principal engineer and now the optical payload manager working on EarthCare. Here we see you amongst the early team. What has been your personal highlight over the years?
I've really enjoyed working on the technology developments for EarthCare. We have some real cutting-edge technologies that we've managed to put onto one platform. It's been quite a challenge, as well as the Japanese radar. We have 3 optical instruments, and each one has come across difficulties, right down to the smallest instrument, which is the broadband radiometer. So the radiometer operates with 3 telescopes, and they're really rather simple telescopes. They're just single mirror telescopes, each pointing to a different viewpoint on the Earth. But they use a detector which makes an image by measuring the difference between the scene and a constant temperature target. And how do we do that? We have a drum which spins around those telescopes, and it has some holes cut in it, which is the view to the Earth. So that chops the signals onto the detectors so that they can make this measurement. But that means that that drum has to spin for the entire mission for several hundred millions of revolutions at very high stability, and it has to do that with a dry lubrication technique. So really it's quite amazing and quite challenging for such a small instrument compared to the other instruments on the other satellite. And we have 4 instruments operating together, and that's what makes the real difference for our mission, the synergy.
It's so incredible to hear. And what is the meaning of EarthCare for your personal career?
For me, it's the first time that I've managed to get to launching a satellite, because normally I move on to another mission after the development. So this is the first mission where I'm working on the launch phase as well.
Well, you definitely deserve to see an excellent launch. Thank you very much, Kotska. And now the last 20 minutes of a 20-year project have begun. Let's take a closer look at these instruments. First up is the European LiDAR.
The atmospheric LiDAR is an advanced light detection and ranging system designed to measure the vertical profile of aerosols and clouds in Earth's atmosphere. By emitting light pulses and analyzing the reflected signals, EarthCare's LiDAR can precisely provide the distribution and properties of aerosols and clouds. This includes their altitude, thickness, and detailed optical properties in aerosol type. This information is crucial for improving climate models and understanding the role of aerosols and clouds in Earth's energy balance.
Georgios Teramis is ESA's principal athlete engineer. Georgios, you know every screw of this instrument by name. Is there still something that impresses you about it?
Well, 1,532 screws and bolts on the satellite. But that's not the important number. There is one number which is far more critical for us, and that's 7.1 billion shots, 7.1 billion pulses. This is the number we need to reach in the UV region during the 4.5 years of mission. It was quite challenging to get there, and we will get there. These pulses are also very narrow. They are about 25 nanometers each. So if we look at how much light we actually emit, it's only for 177 seconds. So through the entire 4.5 years of operations, we will have only 177 seconds of light coming out of this instrument. How do we achieve the science then with this short period of light? Well, Ulla already mentioned that it's a unique instrument which is having the technology called HSRL, High Spectral Resolution Etalon, which is allowing us to separate molecules from aerosols. At the same time, we have something else which was never combined before, and this is a depolarization channel. Mixing these 2 technologies allows us to discriminate excellently between anthropogenic, man-made aerosols and non-anthropogenic, natural aerosols. So every scene that we're looking underneath a satellite can immediately be separated if it's industrial pollution or if it is biomass burning, if it is Sahara dust events, as already mentioned, or something else like volcanic gas. This is a unique capability, never seen before from space, and that's why it's such an exciting instrument.
It's very impressive indeed. Thank you very much, Gorgios. And wait a minute, your son Dimitris is here with us today as well. Thank you for coming, Dimi. So, do you like what your dad is doing?
Hi. Hi. My teacher told us last week that scientists I
think scientists are very curious, right?
Scientists are very curious.
You're doing great. So, do you also want to do something revolving around science like your dad?
Yes, because I find science very interesting, and I also like building things.
Oh, perfect. Then that's a good prerequisite. ESA's talent scouts, look out. So thank you so much for being with us, Georgios and Dimitris.
Thank you.
Thank you.
And let's come back now to the satellite and the next marvel of engineering on board, the radar instrument CPR. It's the first Doppler radar ever flown in space, and it was developed and built in Japan. Let's see what this instrument is all about.
The cloud profiling radar provided by JAXA enables EarthCare to observe the internal structure of clouds. It operates in the millimeter wavelength range, penetrating through clouds and light precipitation. This provides detailed insights into their vertical structure and velocity, particle size distribution, and water content. This radar is essential for studying cloud processes, such as the formation and dissipation of clouds. It also contributes valuable data for improving weather and climate models.
With me now is Kawamura Seiji from the National Institute of Information and Communications. And no, don't worry, we aren't going to start a circus right now. Kawamura-san, the CPR radar is very prominent with its 2.5 meter dish on top. That's about roughly the size of this circle we have here, and the CPR radar we see up there. How did you build this?
はい、この CPR のアンテナ、軽くて丈夫である必要があるんですね。そのために CFRP という素材で作っています。で、このアンテナの表面にはレーダーの電波を反射するためにアルミニウムを蒸着しているんですけれども、当時、20年以上前ですね、 CPR がまだEarthCareに正式に採用される前ですけれども、このような大きなアンテナ 2.5 メートルに対して一度に蒸着するアルミニウムを蒸着するような技術がなかったんです。で、我々これを、分割したアンテナで作ろうというふうに考えました。なので我々はこのアンテナのちっちゃいモデルで80センチの直径のスケールモデルを作りまして、一面のアンテナと分割したアンテナとを使って、それで分割したアンテナがちゃんと動くかという、そういう評価をしていたんです。で、ところが、CPR が正式に採用されることが決まりまして、いざ作るという段階になった時には、この大きなアンテナに一度に蒸着することができるようになっていました。ということで、我々のその試作した、小さいアンテナというのは CPR に使われることはなかったんです。ただ、このちっちゃいアンテナが無駄になったかというと決してそうではなくて、我々は打ち上がった後CPR の検証とか構成をやるんですけれども、この、検証用の、地上設置のレーダー、ダブル体のレーダーを我々作っているんですが、そのアンテナとしてその小さいアンテナは今使われているところです。
And how lucky we are that technology changed in due time to make this instrument happen. Thank you very much, Kawamura-san.
Thank you very much.
Esse uyo. That is Japanese for controlling the satellite, and that's what the team down in the main control room is preparing to do right now. I've been told just a minute ago that our network of ground stations all around the world are standing by, starting with Hatebestu in South Africa, then Kiruna and Svalbard high in the Arctic Circle, right at the top of Europe, continuing round to Alaska and then even Antarctica. We are ready to hear EarthCare. We need them to stay in touch with EarthCare as it flies from pole to pole in an orbit lasting 5,555 seconds, or about 1.5 hours in more normal numbers. And as the globe rotates beneath the satellite, we scan the planet every 25 days, but touching base every 90 minutes with our Nordic ground stations to download that precious data.
Walter Pelzer is with me now, hopefully. He's coming on stage. He is the Director General of the German Space Agency in the DLR. Walter, the control center is in Germany. EarthCare is designed and integrated in Germany. Major science institutes are involved, and the DLR flies a validation aircraft and hosts a number of data networks. How does Earth observation rank in the German space agenda?
Well, I think, hello again, first of all, and I think we had this similar question already. Yes, a lot of the footprint of Germany in Earth observation is pretty high. The German ranking, or German ranks Earth observation on top of this list, whether it's in money-wise, whether it's staff-wise, and also in our space agency. So from this point of view, Earth observation is core when it comes to tackle the great challenges, climate change, other grand challenges we are facing on Earth. And I mentioned already earlier today that Germany is doing space to make life on Earth better. So from this point of view, it's #1 ranked in our space strategy. And so from this point of view, EarthCare and this mission is #1 when it comes and when it comes to close to our heart.
Fantastic. Thank you very much, Walter. Keep up the pace. The world surely needs it.
Let's cross the finger for the mission.
Now, all ESA projects aim at one goal, serving the people on our planet. But is this recognized? And I want to ask the science communicator, Dr. Fission, about this. He runs the second largest Spanish science channel with an incredible 9 million followers. Doc, do people know what ESA is doing to take care of our climate?
Yes, absolutely. I have a feeling that people think that we are not doing
Nice launch trajectory and countdown net. Pad is clear.
10, 9, 8.
Launch auto sequence has started.
6, 5, 4, 3, 2, 1.
Go for launch.
Vehicle is supersonic.
Stage separation confirmed. Dragon, separation confirmed.
Stage 1 is transonic. Landing legs have deployed. And Falcon 9 has landed.
Hello everyone, it's Tuesday, May 28th, and you're looking at a live view of our Falcon 9 rocket awaiting its 3:20 p.m. Pacific Time launch from Slick 4 East at Vandenberg Space Force Base in California. Today's launch marks SpaceX's 56th mission of 2024 and the 340th overall Falcon 9 mission to date. My name is Zachary Lupin, and I'm an avionics reliability engineer here at SpaceX, and I'm joining you from our headquarters in Hawthorne, California. Welcome to our live launch coverage of the EarthCare mission, a European Space Agency Earth Explorer mission developed as a joint project between ESA and the Japan Aerospace Exploration Agency, or JAXA. Now, the CARE in EarthCare is an acronym that stands for Cloud Aerosol and Radiation Explorer. Once in space, EarthCare will collect data to answer questions about Earth's radiation balance, which is a key factor in regulating Earth's climate. It will also measure vertical profiles of cloud particles and aerosols and their fall speed, or the speed at which the particles and aerosols fall through the air. This data will be used for climate research and will improve the accuracy of climate models and support weather predictions. We'll have more to share about today's payload later on in the webcast. Currently, both the vehicle and range are green, and we are on track for an on-time launch at 3:20 p.m. Pacific Time. For now, let's meet the vehicle and learn a little bit more about the most flown U.S. launch vehicle ever, our Falcon 9 rocket. Falcon 9 is a two-stage rocket developed and manufactured by SpaceX, known for its safe, reliable, and cost-effective access to space. It is also the first and currently the only orbital-class rocket capable of reflight. Starting at the top of the vehicle is the payload fairing, a protective shell that encases the payload being sent to space. That fairing will separate and jettison away from the vehicle, exposing the payload once Falcon 9 reaches space. Today's payload, currently encapsulated in those payload fairings, is ESA's EarthCare.
The spacecraft is on internal power.
ESA's EarthCare satellite. Equipped with 4 primary instruments, EarthCare will make a range of measurements that together will shed new light on the role that clouds and aerosols play in regulating Earth's temperature. The mission's data will be used for climate research and will improve the accuracy of climate models as well as support higher fidelity numerical weather prediction. Continuing down the vehicle, we have the second stage. Now, the second stage is powered by a single Merlin vacuum engine, or MVAC, which is optimized to perform in the vacuum of space. After stage separation, the MVAC will ignite and carry the payload to its final orbit. The Falcon 9's first and second stages are connected via the black inner stage, which houses the MVAC engine and the system that decouples the two stages during stage separation. And below that is the Falcon 9 first stage, which is powered by 9 Merlin engines. These 9 Merlin engines provide the initial thrust to lift Falcon 9 off of the ground through the lower, thicker part of the atmosphere. And there are 8 engines arranged around one center engine, which are held in place by a structure called the octaweb, a shape designed to maximize efficiency. Now, each of these Merlin 1D engines delivers about 190,000 pounds of thrust at sea level, which gives Falcon 9 a combined 1.7 million pounds of thrust. After stage separation, Stage 1 will return to Earth for recovery and reuse on a future mission using a combination of the Merlin sea level engines and the 4 titanium grid fins located near the top of the booster, which will guide it during its re-entry and landing.
Our Earth is a complex system. To protect it, we need to fill in the missing piece of the climate puzzle. How do clouds and aerosols affect Earth's energy balance? While we know that they play extremely important roles in regulating our atmosphere's temperature, we don't know how their behavior will change as our climate warms. This is where EarthCare comes in. ESA's Earth, Cloud, Aerosol and Radiation Explorer will shed new light on how clouds and aerosols affect our climate. With its suite of 4 cutting-edge instruments, EarthCare represents a groundbreaking advancement in satellite technology. It promises to deliver unprecedented data, unraveling the complexities of clouds and aerosols. With this, we can refine our atmospheric models and climate forecasts, giving us the tools to tackle the challenges of a changing climate with greater accuracy and precision.
Tonight's launch is a reminder that space is not only about exploring distant galaxies and planets. It is about understanding our beautiful but fragile Earth so we can protect it and improve life on our home planet. EarthCare is a groundbreaking mission developed by the European Space Agency in collaboration with JAXA, the Japanese space agency. It is thanks to this collaboration that we have been able to build such a sophisticated satellite. I should like to personally thank all the teams involved who designed and built the satellite and got it where we are today. They have shown a major commitment of time, talent and tenacity. I appreciate your dedication and share your excitement tonight.
I'd like to personally thank all the teams involved who designed and built the satellite, and to get it what we're here today, EarthCare comes at a time perfect for climate science and climate communities worldwide. Let us seize this opportunity to deepen and expand our knowledge and to chart a course towards a more sustainable future for all of us. Go EarthCare!
As you just saw, there's some really exciting science set to happen on this mission. But first, we need to get it to space. Now, in order to get the rocket and payload into any orbit, the rocket has to not only go up really fast, but it also has to go sideways. And as the rocket ascends, we'll tilt the engines, and that'll turn the rocket horizontally into what's known as a gravity turn. To help demonstrate this concept, we'll use an analogy popularly attributed to Sir Isaac Newton, who was the first person to formulate a comprehensive theory of gravity in his 1687 Law of Universal Gravitation. Newton asked to imagine firing a cannon from a really high mountain. The cannonball will arc, and then gravity will pull it down to Earth. Now, as you increase the power of the cannon, that cannonball will arc and land farther and farther away. Eventually, if you could continue to increase the power, the cannonball will end up in free fall around the Earth. Essentially, gravity is pulling down on the cannonball, but because of its speed and the curvature of the Earth, it never hits the ground. And this arc that constantly misses the Earth is called an orbit. Modern rockets like the Falcon 9 operate on the same basic principles of gravity and orbital mechanics that Newton described, but with modern technology. And Falcon 9 provides enough power and horizontal velocity to place its payload in orbit above the Earth.
Tanks are pressing for strongback retract.
Good call out there. You'll be able to see this today by watching the orientation of the Falcon 9 after liftoff. The rocket will go straight up until about the T plus 10 second mark, at which point we'll begin a shift towards a horizontal orientation from gimbaling the engines. So be sure to look for that after liftoff. Coming up shortly, the Transporter Erector, or TE, will retract away from Falcon. The TE is the large truss structure you see there next to the rocket. First, we'll see the clamp arms open around
retract has started.
Around the second stage, and then the TE will pull away from the rocket by roughly 77 degrees. Now that first stage is connected to a launch mount at the base of the TE, but the TE is hinged and will retract away from the vehicle in preparation for launch. You may hear the TE referred to as the strongback from the launch team, and it does a lot of heavy lifting in the lead up to launch. It's designed to transport, raise, and support Falcon 9 at the launch pad. The TE is also equipped with umbilicals or flexible lines that are used to route the vehicle's fluids, power, and telemetry from the ground systems to the rocket and payload until Falcon 9 switches to internal power and clears the pad. And as you can see on your screen there, the strong back is retracting away from the vehicle. At this point in the countdown, both the first and second stages are nearly fully loaded with 1 million pounds of rocket-grade kerosene fuel and liquid oxygen. Both the first stage and second stage should finish propellant loading about a minute apart from each other, with the first stage finishing up at around the T-3 minute mark, and the second stage finishing at the T-2 minute mark.
Stage 1 LOX load is complete.
And there's that call out that Stage 1 LOX loading has completed. As you may have noticed, there are white clouds forming around the vehicle. Those clouds are comprised of the chilled gas above the LOX tank that is vented overboard to maintain pressure in the tank as needed. And when that vented oxygen mixes with the warmer California air, it condenses into clouds. At the T-60 second mark, Falcon 9 will be in startup, and this means that the rocket's autonomous internal flight computers will have taken over the launch countdown, and then just inside of T-2 seconds, we'll light the M1D engines for liftoff. The EarthCare payload continues to be healthy, and the Falcon 9 team is tracking no issues on the rocket. Weather is still looking green, and the range is ready to support our T0 of 3:20 p.m. Pacific time. And with that, we're proceeding into the last couple minutes of terminal count.
Stage 2 LOX load is complete.
And there's that call out that Stage 2 LOX loading is complete. Falcon 9 is now fully loaded with 1 million pounds of propellant and oxidizer.
Ground gas closeouts.
Good call out there. In about 20 seconds from now, we should hear a call out that Falcon 9 is in startup. And as a reminder, this is a call out that the rocket's autonomous internal flight computers have taken over the launch countdown.
Falcon 9 is in startup.
And there's that call out that Falcon 9 is in startup. Lastly, we're waiting for the launch director, or LD, to give the final go for today's launch.
LD is go for launch.
And with that call out that the LD is go for launch, we are set to launch ESA's EarthCare payload.
T-minus 30 seconds. T-minus 15. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, ignition, power, and liftoff. Go Falcon 9, go EarthCare. Vehicle pitching coverage. Stay ground chamber pressure nominal.
At T plus 30 seconds and counting, Falcon 9 has successfully lifted off from Slick 4 East carrying the EarthCare satellite. Now, after clearing the tower, we tilted or gimbaled the engines to initiate a roll maneuver, which you may notice in the Stage 1 camera view. This enables the vehicle's antennas.
Telemetry nominal.
This enables the vehicle's antennas to stay in the best position for communicating with the ground. In just a few moments from now, we'll be throttling down the engines in preparation for max Q, or maximum aerodynamic pressure.
Vehicle supersonic. Max Q.
And And there's that call out for max Q. Now, as Falcon 9 accelerates through the thicker lower atmosphere, the air density decreases, and Falcon 9 passes max Q once the air density lowers faster than the increasing speed of the vehicle. So keep an eye on the Stage 1 telemetry on the bottom left-hand corner of your screen to watch for these speed changes through ascent.
And back chill.
Good call out there. And as a reminder, the rocket typically needs to go 17,500 miles per hour horizontally in order to avoid being pulled back down to Earth and get into orbit. Now we've got 6 events coming up happening in rapid succession. This will start with main engine cutoff, or MECO, where we shut down all 9 M1D engines on the first stage. Followed by that will be stage separation, where the first and second stages separate. Third will be the stage 1 flip, a maneuver to turn the first stage around. Then we'll have the second engine start, or SES1, on the second stage. Fifth will be the first stage boost back burn, a controlled burn that reduces the forward velocity away from the launch pad. And lastly will be fairing separation, where the 2 fairing halves will jettison away from the second stage. And all of these events should happen in just a few moments from now.
MECO.
Stage separation confirmed.
And vac ignition.
Stage 1 boost back burn.
Fairing separation confirmed.
And there you heard and maybe even saw those 6 events that happened back to back, which again were MECO, stage separation, stage 1 flip, second engine start 1, the first stage boost back burn, and fairing separation. We'll be attempting to retrieve those fairing halves, both flying for their first time today, once they fall back to Earth with our recovery vessel, Go Beyond. Coming up shortly, we should hear a call out for boost back shutdown on the Falcon 9 first stage.
Stage 1 boost back shutdown.
And there's that call out for stage 1 boost back shutdown. We're currently T+3 minutes and 34 seconds into the mission. Our next major mission milestone will be...
Both vehicles are following nominal trajectories.
Good call out there. Our next major mission milestone will be the first stage's entry burn, which will take place just past the T+6 minute mark. Now, to start the entry burn, we will relight 3 of the M1D engines on the Falcon 9 first stage, which is similar to pumping the brakes to slow down the vehicle as it passes back into the Earth's atmosphere. The entry burn helps reduce the heat generated from the friction of the atmosphere and reduces the aerodynamic forces acting on Falcon, which helps maintain controlled flight and prepare for the landing burn. Now, during the entry burn, Falcon 9 is decelerating by firing its Merlin engines, but it's still moving really fast, and this causes the vehicle to fly through Merlin's exhaust gases, or plume, which deposits a layer of soot on the vehicle surface. And that soot comes from the carbon-based fuel that Falcon 9 uses, and with each flight, the soot builds up a little more on the outside of the vehicle. Some amazing views of the MVAC engine on our Falcon 9 second stage as it takes the EarthCare payload to orbit. Reusability is key to lowering the cost of spaceflight, which enables more investments in critical scientific research. Now, the Falcon 9 first stage that is supporting today's mission is performing this entry burn for its 7th time, coming up shortly. Now, the Merlins on the first stage are optimized for sea level, and these achieve 190,000 pounds of thrust each during ascent and descent. At liftoff, Falcon 9's first stage has thrust greater than 5 747 airplanes at full power. And the MVAC engine on the second stage, with a much wider nozzle, is optimized to 220,500 pounds of thrust in vacuum. Now, as a reminder, the first stage supporting today's mission is flying for its 7th time, having previously supported NASA Crew 7, CRS-29, PACE, Transporter 10, and 2 Starlink missions. It's also worth mentioning that this is the 56th Falcon 9 launch of 2024 and the 18th launch of Falcon 9 this year from Vandenberg Space Force Base in California. Coming up in just a few moments, we should hear the call out for the entry burn on the Falcon 9 first stage.
Stage 1 entry burn startup.
And there's that confirmation of entry burn startup. This burn will last about 20 seconds and will slow the vehicle down in preparation for the landing burn.
Stage 1 entry burn shutdown.
And there's confirmation of Stage 1 entry burn shutdown. We're now waiting for Falcon 9 to land back at Landing Zone 4 at Vandenberg Space Force Base in California. And it just so happens that Landing Zone 4 is actually only about 450...
Both vehicles are on nominal trajectories.
Good call out.
Stage 1 FTS has saved.
Good call-outs there. It just so happens that Landing Zone 4 is actually only about 440 meters away from Slick 4 East at Vandenberg.
Stage 1 transonic.
Good call out there that Stage 1 is transonic. We should hear a call out for landing burn startup on the Falcon 9 first stage in just a few moments.
Stage 1 landing burn. Stage 1 landing light deployed.
And there you have it. Falcon 9 has successfully...
Stage 1 landing confirmed.
Falcon 9 has successfully...
Stage 2 FTS is saved.
Stage 2 is in terminal guidance.
Good call-outs there. Falcon 9 has successfully landed at Landing Zone 4 at Vandenberg. This was the 7th launch and landing for this first stage. And this landing marks SpaceX's 314th recovery of an orbital-class rocket, including first stage landings for Falcon 9 and Falcon Heavy. Coming up next, we'll hear a call-out for SECO 1, or Second Engine Cutoff 1, on the Falcon 9 second stage, currently on your screen.
MVAC shutdown.
And there's that call out for MVAC shutdown on the second stage. We're now waiting for confirmation of nominal orbital insertion.
Nominal orbit insertion.
And there's that call out. Now with that call out, we're just one major milestone left in our mission, which is payload deployment, coming up in about a minute and a half from now. Now, Earth Explorer missions like this one are state-of-the-art science and research missions that deliver data to fill gaps in Earth system science and demonstrate new space technologies. EarthCare is the largest and most complex Earth Explorer satellite to date. The satellite carries 4 state-of-the-art scientific instruments that work together to provide a holistic view of the interplay between clouds, aerosols, and radiation, a cloud profiling radar, an atmospheric LiDAR, a multispectral imager, and a broadband radiometer. Together, these instruments will allow scientists to better understand the processes governing the physics and interaction of clouds and aerosols and their impact on Earth's temperature. We're expecting payload deployment of the EarthCare satellite in just under 40 seconds from now. As a reminder, this is the 56th Falcon 9 launch of 2024 and the 18th launch of Falcon 9 this year from Vandenberg Space Force Base in California.
EarthCare separation confirmed.
An amazing view there on your screen. Successful deployment of the EarthCare payload. And with that confirmation, we'll be bringing today's webcast to a close. Today's mission marks SpaceX's 351st overall mission to date and 56th mission of this year. We want to thank the European Space Agency and JAXA for entrusting us with today's mission, and all of you for joining us this afternoon. If you're interested in following the EarthCare mission further, tune into youtube.com/ESA for more. And if you're interested in more launch coverage, be sure to check out spacex.com/launches for the most up-to-date information. Thanks for tuning in, and we'll see you again soon.